Number 5. Let's get ourselves a long problem to work on here. Oxygen gas can be generated by strongly heating mercury 2 oxide according to the following equation. Oh my gosh, look at all that useless information. Again, when you guys are working on these types of problems, especially when you're getting into the mode that where you're taking an assessment, a quiz, or a test, remember, try to make your world small. Okay, try to make your world small. Cut out any of the stuff that isn't useful to you. Remember that on a quiz or on a test, I'm not going to introduce a whole bunch of crazy new situations. A quiz or a test is an assessment. Remember what an assessment is. It's assessing how you're doing with the content. Which begs the question, what content? The content that we've been practicing in class with the lecture, with the reading of the textbook, with the preparation problems, practice problems, sample problems, with the worksheet problems. All the stuff that you've already been doing. Remember, if you read a question and you get confused, reset the whole system, and remember, in order to get this point, you're going to have to do something that we've done in class in order to get that point. Okay? So think back to the things that you have done in class and think which one applies to this situation. Case in point, oxygen can be generated by strongly heating mercury 2 oxide. Do you need to know that? No, you don't. You don't need to know the extensive properties of mercury 2 oxide. You don't need to know when this equation is used in industry. You don't have to know it. It's completely useless per se. What is useful is this balanced chemical equation, right? So be aware of what the question is giving you just so that you can know what to pay attention to and what to not pay attention to. All right, part A. If 15.0 grams of that mercury 2 oxide decomposes, right? Decomposes. This is breaking apart, right? 2 moles on this side of the reaction arrow, 3 moles on this side of the reaction arrow. That's the decomposition reaction. But if 15 grams of it decompose, how many moles does that represent? All right, so I'm doing a simple molar mass conversion. That's pretty darn easy. So the question gives me 15.0 grams of HGO to start with. And so I'm going to convert out of HGO and into moles of HGO or HGO. And that's what the question is asking for. So let's see how many grams are in 1 mole. Now, I never seem to remember how many grams are in a mole of mercury. I don't know why. It's a pretty even number. 200.59 plus 1 oxygen. That seems about right. 216.59. Now the question gave me 3 significant figures to start with, so my answer is going to be in 3 significant figures. So let's see what we get here. 15.0 divided by, oh my gosh, this is going to be a number that is less than 0. Holy cow, yes, that is less than 0. But to 3 significant figures, I'm going to round to that 2 right there. What does that number right behind it tell me to do? Round it up. So I'm going to report 0.0693 moles, right? It's going to be moles because those grams of HGO cancel, leaving only moles as my unit. Fair enough? Part B. How many moles of O2 are theoretically produced? Remember, we use ideal conditions to establish the theoretical yield. So under ideal conditions, how many moles of H2 would be produced? According to what? Oh yeah, this amount. Okay, this amount. If this many moles of HGO decompose, how many moles of O2 would be produced theoretically? Now, there are two different ways that you can start this problem. One, you can start from the 15 grams of HGO and convert into moles of HGO, and then use the mole ratio of HGO to O2 to generate your answer. Or, because you've already generated the number of moles of HGO, you can start with the moles of HGO and just use the mole ratio of HGO to O2, which is 2 to 1, 2 to 1. Right, moles of HGO cancel. I'm in moles of O2. I've made myself a simple one-step calculation. But again, if you wanted to start all the way back from the 15 grams of HGO, that would totally work as well. You just also need to include this conversion factor back here at the beginning of this setup, right? You'd have to slap this extra conversion factor on the beginning of this. Still get the correct, same correct answer, just be a little bit longer. So 0.0693 times 1 divided by 2. We end up with, again, going for 3 significant figures. Why? It says 3 significant figures, so I'm going to round to that spot. What does that tell me to make it? 0.0347. Okay, and what are my units? Moles of O2. So 0.0347 moles. Okay, that's how many moles of O2 would theoretically, ideally be produced. Is that amount going to be produced? No. Okay, in real conditions, you're going to get some amount less than that. How many grams is this? Whoa, okay, that's not so hard. I'm going to go from moles of O2 and convert out of moles of O2 and into grams of O2. All right, so that would cancel moles of O2. My answer would have units of grams of O2, which is perfect because I'm being asked for grams of O2. But how many moles of O2 did I start with? Okay, and what's my molar mass here? That's a diatomic molecule, so 32. All right, so I'm still doing 3 significant figures, so what should I turn that into? I'm going to have to round to that spot right there. What does the number right behind it tell me to do? It tells me to round it up. So I got 1.11 grams of O2, 1.11 grams of O2. Part D. If the density, oh my gosh, I don't know a lot about density. It's so intimidating. It's weird. Like, how do I know about it? If the density of O2 gas is 1.41 grams per liter, this is an item that lets us convert between grams and liters, right? Foreshadowing, spoiler alert, how many liters of O2 are produced? Notice we just generated grams of O2. We now have a number that allows us to convert between grams and liters. What is this question asking us for? How many liters? Oh my gosh. So we're going to start with those grams of O2 and convert out of grams of O2 and into liters of O2. Well, how many grams per 1 liter? Right, per 1 liter, per 1 liter, 1.41. How many grams do we start with? We just figured that out in part C. Grams of O2 cancel. Plug this into the calculadora. Oh, I messed that up. 1.11 times 1, just for completeness, divided by 1.41. Let's see. I'm still doing 3 significant figures, so I'm going to round to that spot right there. The number behind me says to leave that the same. So I'm going to go with 0.787. And what are my units? Right? Grams cancel, grams cancel. Liters of O2. Part E. if the percentage yield is 95%, okay, remember, percent equals actual over theoretical. If the percent yield is 95%, or if I wanted to put that in terms of a decimal, 0.95, how many grams of O2 are actually produced? I'm being asked for actual yield. So that means I've been given this, so check that off. I'm being asked for this, but where do I get this? Right? Oh yeah, that's what I already generated right there. How many grams is this theoretically producing? How many grams is this theoretically producing? That's my theoretical yield. So, again, I'm trying to solve for actual. So, in order to solve for actual, let's rearrange this. Multiply both sides by theoretical. The way theoretical cancels, and I have actual, okay, actually collect, that's what I'm solving for, equals my theoretical yield multiplied by my percentage. So let's plug those in. What's my theoretical yield? 1.11. 1.11. What is my percent yield? I'm actually getting 95% of that. I'm actually getting 95% of that. So, let's see what that ends up being. 1.11 times 0.95. Kind of a small number. Oh my gosh, that doesn't make sense. Look, I typed in a divide instead of multiply. Silly Mr. Johnson. Let's try that again. Okay. Again, start with 3 significant figures. Let's use 3 significant figures. Here's 3 significant figures. Let's use 3 significant figures in our answer. 1, 2, 3. Number behind it tells me to keep it the same. So I end up with 1.05 grams. How much is actually collected? 1.05 grams of O2.